Okay, so let's consider the sampling, I guess, a sample size of 2 from a normal distribution, and then we'll extend that to a sample size larger than 2. All right, so we know from the previous exercise that if we sample from a normal distribution, well, then the mean and the variance of that distribution is also normally distributed. Okay, so if X is a normal distribution with a random variable with a mean, mu, and a standard deviation sigma. Okay, now it could be IQ scores, rope lengths, or whatever. So if I take a sample size of 2, what's the mean and the standard deviation of that sample size of 2? Well, the sample mean is simply the average, x1 plus x2 on 2. So now if we consider what the expected value of that average and the variance of that average are, well, the expected value is just e of x1 plus x2 on 2, which is just the average there that we had. Well, we know that this is a linear combination, so the half can come out the front, and I've just got e of x1 plus e of x2. So the expected value of x1 plus 2 is the individual expected values times by a half. And obviously very quickly we get mu plus mu, which is 2 mu times a half. So as we sort of expect, if we've got a sample of 2, the expected value, okay, is just the average of those 2, which is just the original mu value itself. What about the variance? So the variance of x1 plus x2 on 2, again, it's a linear expression. So we know that that half can come out the front, but it's a half squared. So that gives me a quarter out the front, variance of x, okay, x1, x2. We know that the variances are the same, so sigma squared. So if I add them up, I end up with sigma squared on 2, which means that's the variance. So if I get a standard deviation, it's the square root of that, which is sigma on root 2. So if I had a sample of 2, my expected value is mu, my standard deviation is sigma on root 2. So how does that play out? Let's have a look. So let's say we're talking about our IQ students, okay, mean of 100 and standard deviation of 15. So what's the probability that any randomly selected individual has an IQ greater than 115? All right, so the probability that X is greater than 115, we can go straight to our normal CDF, 105 to infinity, mean 100, standard deviation of 15, gives me 0.1587, which is about 1 standard deviation above, which is 16%, all right? What if I select 2 randomly selected students? Okay, so if I randomly select 2 students, I've got the expected value is 100, and I know previously the standard deviation is 15 on root n. N is 2 in this case, sample size. So the standard deviation in this case is 15 on root 2. So if I want my sample mean to be greater than 115, so the mean of the IQs of the 2 students that I've picked to be greater than 115, normal CDF, 115 to infinity, mean is 100, standard deviation is 15 on root 2, and that gives me a value of 0.0787. So it kind of makes sense, doesn't it? So what we're saying is the probability of one student, okay, having an IQ of greater than 115 is 0.1587. Now, the probability of the average of their IQs for 2 students to be greater than 115 is significantly less. Okay, so, and that's what we're saying. The probability that the mean IQ is greater than 115 is much smaller than that of any individual's IQ is greater than 115. All right. What about if we have sample sizes larger than 2? All right. It can be really easily shown that these 2 formulas hold. All right. The sample mean is not going to change. We've just got a whole heap of mu's, in fact, n of them, divided by n. So the sample mean is still going to have a mean of mu. The standard deviation we can show is sigma over root n, where n is the sample size. So in the previous example, it was sigma on root 2, because we had 2 samples. If I have 10 samples, it's going to be sigma on root 10. All right, that's how the standard deviation is impacted the more sampling that we do. All right. So important thing is, if X is a normally distributed random variable with mean, mu, and standard deviation sigma, then the distribution of the sample mean will also be normally distributed. Okay, and we sort of saw that with the bar charts that we got when we got sample groups. All right. So in other words, when we're sampling from a normal distribution, we can treat the sample values as also a normally distributed variable. All right, with the mean mu and a standard deviation of sigma on root n. All right, so let's have a look. So if I have a machine produces nails which have intended diameter mu is equal to 25.025, there's my mean, and a standard deviation of that diameter is 0.003. Okay, the diameter is normally distributed random variable. All right, now if I wanted to work out the probability of any one, okay, if I want to undo that, if I want the probability that any one nail has a diameter of greater than, well, actually I know what that is, isn't it? And I know that's a half because that's the mean. So the probability, so I would say that it was normal CDF, let's go with 25.025 to infinity, 25.025, and the standard deviation is 0.003. All right, so that's just for one observation. What if, as in this case, I take a sample of 5 nails and their average diameter is calculated? So I'm going to work out the average diameter of the 5 nails together. All right, well, what's the distribution of that result? All right, so that distribution, well, the mean of the diameters is going to be 25.025. Okay, so that's the expected value, I should say, all right, of the sample size. The standard deviation of that sample size is 0.003 over square root 5. All right, so that average, the average of the 5 nails, the average of its diameter is distributed by those variables. So now X bar, the probability that the sample average diameter is greater than 25.027 is given by normal CDF, 25.027 to infinity, the mean of the distribution, which is 25.025, the standard deviation of the distribution, which is 0.003 over root 5. So it's standard deviation that gets affected. So the probability that that particular sample size has a mean diameter of greater than 25.027 is 0.06. All right, so hopefully you're starting to get a feel for what the mean of the distribution is. It's the probability that the sample that we're dealing with satisfies a certain condition. Okay.